Good morning, everyone. Thank you for attending my presentation. So I'm Victor, and today I will present you my research work on design optimization of multi-use components for floating offshore wind turbine. So Sandrine gave us already a broader context, but I will re-put everything a bit into context. So I am ESR number 8, so studying multi-use design components for floating offshore wind turbine substructure, and I'm part of work package 7, which main objective is to reduce the levelized cost of energy of floating offshore wind. And to put things back in perspective, so I'm from the University of Rostock, which is based in Germany, on the coast of the Baltic Sea. And I also circle GICON, which is a group we have a strong cooperation with the University of Rostock and the chair of wind energy technology. So again, another little introduction to the context of floating offshore wind. This is a little analysis we performed during one of the secondments, so in the internship Sandrine was talking about a bit earlier. And we assessed the potential of floating offshore wind in Europe. So it's no surprise to us that there is a big, even maybe a huge potential of floating offshore wind in Europe. So here you can see the different type of water depth in Europe, and also some area of potential floating offshore wind site in Europe that we were able to assess. So we did this study with Thomas and Xiaoming, which are also here. And so that's a nice example of the collaboration we had between the ESRs. I'm sorry a bit the presentation lapse every time, but it's no problem. So with floating offshore wind, we saw that there is a higher wind speed and extreme sea state when compared, of course, to onshore wind. So this leads to a different type of floating substructure. There is no consensus on which substructure is the best to put where or in different sites. So that's one thing to consider. Those substructures are complex to manufacture, and the installation process and all the context around floating things in offshore environments is difficult. And this leads eventually to high LCOE. We saw it with the presentation of Craig and the minimization Kutai is trying to do with his work. So at the University of Rostock, there is a solution for that, or at least we study a solution to cope with that. So as I said, there is a strong collaboration with GICON. So here is a GICON TLP. So it's a steel and concrete tension leg platform. So a tension leg platform is one type of substructure for floating offshore wind. As you can see, it has an evolving design. So this is the design which evolved, I believe, in the past 10 years. They've been developing this substructure. So with the early stage design to a more up-to-date design, which I am going to talk about more in detail. So it's composed of mainly buoyancy bodies and steel pipes, vertical and diagonal and horizontal, as you can see on the picture. The main advantage of this substructure is that it's simple to manufacture, to install, to tow out offshore, and the installation process. So far at the university, numerical and experimental analysis have been performed, so in the basin test and also numerical models have been developed. And I guess the main objective of my study and my research was to develop a design optimization framework with regard to this substructure, but also other substructure, and also multi-use components, which was in the title of my presentation and which I will show right now. So behind the term multi-use components, we think of components that could be adapted to, that could be easy to manufacture, to use for in-series production of substructures, but also for different type of substructure. So TLP, but also semi-submersible, or maybe even spar substructure, as Kutai was broadcasting. So we at the University of Rostock and GICON, we came up with this technology, the universal buoyancy body. So as you saw in the GICON substructure, there are many buoyancy bodies which are at stake, and they came up with a simple design and manufacturing process for such a components, which is inspired by tower and monopile design. And so, therefore, which doesn't need a specialized manufacturing site compared to other maybe components. And the design is simple, and it also takes advantage of fewer welded components. So I won't go too much into detail, but it's a sandwich type design with concrete and steel to replace the use of stiffeners or decrease the use of stiffeners in the design. Also, it allows you to have a final integration at a yard or a dock, and that's also how where comes the multi-used components thing aspect to include final integration for different type of substructure. Okay, so one example of multi-use components for a floating substructure. The Gcont LP and the universal buoyancy body is one of the main aspects of my research, and so as I said, I was developing a design optimization framework, which is not solely focused on this substructure, but was developed for this substructure and could be extended to other substructure as well later on. Okay, so what is a good design optimization framework? First, you need an optimizer to perform the optimization, but you also need a numerical model to assess what you are assessing, in our case, floating offshore wind turbine. You need a parametrization. We saw it with Kutai with the draft of the SPAR. So you need the parametrization to tell the optimizer what you're going to change in your substructure and to eventually find the optimized substructure. You need objectives to drive your optimization, but you also need constraints to prevent the optimization to get lost in the design space. Okay, at the very beginning of my research, we've performed the state-of-the-art on design optimization focused on floating offshore wind turbine and a bit more focused on substructure design. And we came up with solutions. Oh, there's a little flip. So for design optimization framework to be nice, it needs to be efficient, but also accurate. And we decided to use a frequency domain for the numerical model to kind of co-op with efficiency and accuracy. We've decided to use genetic algorithm for the optimizer because it's a well-used type of optimization in floating wind turbine. The parametrization will be on the substructure geometry and the buoyancy body geometry. The objective is to lower the mass of the substructure and therefore the cost, the material cost. And the constraints are on the system's dynamics because if you have a floating wind turbine, you don't want it to have a crazy dynamic. And so the constraints will take those in consideration. Okay, I will briefly explain the numerical model we use, and then after the optimization. I will finish by giving some results, and then we will pass on to other presentation. So we use the raft model. So the response amplitude for floating turbine, it's a code developed by NREL. It's a frequency domain dynamic code. So it includes all the system of a floating wind turbine. So the aerodynamics are using a quite classical method, so a steady-state blade, elementum, momentum, using CC blade, another open source code. The hydrodynamics are based on the strip theory, so the Morrison equation, but you can also use potential flow using HAMS, so the software was mentioned a bit earlier. And the moorings is a quasi-static model given also by MoorP, which is a Python adaptation of Moordin. So the code have been verified against time domain simulation and accord quite well. And it's an open source Python code, so it's really nice. It's open source, you can use it, and you can also build on it. And that's why it was chosen to be used. So to give you a classical recipe of how raft works, once you have defined an environmental conditions, so sea state, wind speed, things according to that, and also a design of your substructure, you can compute static properties and mean loading on your system. So that's a quite nice picture of a raft, and you can see all the different elements of the floating wind turbine. Based on that, you can solve for the mean position of your system. So basically, all the mean loading on your system, you can then compute an offset of your system, so which give you an offset position of your whole system. Then on this position, you can compute all frequency-dependent matrices and components based on this position and linearize it to get the excitation and damping from mainly sea state, but also aerodynamic excitation. And then this is the quite known equation of floating system, including all the components I was talking about. And you can iterate this equation to to converge all frequency-dependent terms, and then you get the description of the dynamic of your system in the frequency domain. And by combining the mean offset and the statistical representation of your dynamics, you can estimate maximum dynamic element of your system. So the maximum estimated pitch, heave, motion, surge, offset, etc., etc. Also tensions in the mooring lines and a few structural quantities such as the tower-based bending moment, which will be used a bit later. I will go quickly on that. So it's the parametrization I will use in the later example. So you recognize a bit a cut view of the J-Conte LP. So with the top of the wind turbine over there and the mooring lines down there, and the buoyancy body. We decided to only use the diameter of the buoyancy body, its length and center in the horizontal, vertical position of your floating system. The rest is fixed, so we use the 15 megawatt wind turbine and classical mooring lines for a TLP. I give a few figures there, but yeah, this is fixed. Optimization. I will briefly go over how the optimization go using genetic algorithm. I will go a bit classical in the first time and then get a bit more in the details of our optimization. So genetic algorithm or population-based, you have to imagine that this is a population of all the potential designs you're studying. What you do is that you give a fitness to every design. So you can tell which design is based on what. So remember that we use the mass of the substructure. So the lower the mass, the best the fitness will be for a potential design. It's nice to use genetic algorithm because you don't need derivative. So you can kind of close your eyes and, okay, let's go for optimization. And it's simple to use and implement. It also has some drawbacks, which I will go over later. It's not guaranteed that you will attain the global optimal in all your design space. And maybe sometimes you're going to compute fitness of an individual, which is not good. And so it's kind of a waste of time to do that. So you start with an initial population. Basically, how genetic algorithm works is that you start with an initial population. You then make a selection, hoping to select the best designs in your population. And with crossover operation and mutation, so by adding the characteristic of two selected designs, you hope to obtain a better design, or you try to look somewhere in your design space for some other place where you're going to have maybe or maybe not a better design. After a couple iteration, you might get new population all over your design space. But like I said, we had some problems because maybe you looked somewhere it was not worth it looking at in your design space, and maybe it was worthless. To cope with that, we've used some classical method inspired by other genetic algorithms. So a fitness scaling operation and also an addition operation. So the fitness scaling allows you to scale the fitness, so between 0 and 1, I was showing, to account for maybe density in your population and also closeness between individuals. It allows you to scale the fitness to different optimum in your population and to get rid of the problem of getting trapped in one local optimum. The addition operation allows you to prevent the unnecessary fitness function evaluation. So I will briefly give an example. So if we zoom in on our design space, so those are the new individuals we might be tempted to compute and to add to our population. So we use the distance criteria. So if, for example, I take one individual and I want to add it to my population of my genetic algorithm, I'm going to look if it's in the area of a low fitness individual or a high fitness. The higher fitness my individual will be, the less the distance criteria will, the smaller distance the distance criteria will be, because I want to have individual in the interesting place of my design space. Whereas in the opposite, low fitness area of my design space, I want a bigger distance criteria because in the end, I don't want to look in this position of my design space because I kind of know that in this area, I have low fitness people. Okay, and so if you repeat this, you get a higher density of individuals in the more interested area of the design space. Okay, to kind of globalize the optimization framework I just presented, this is what it looked like. You recognize the optimizer right here and the numerical model that are here. What is good with genetic algorithm is that it's highly parallelizable. So we use Python to implement this framework. Like I said, it's easy to use multiprocessing with genetic algorithm to speed up the process of optimization. You have a modular approach, so you can plug in some other numerical model or some other boxes to your framework to make it better. So easy to build on and easy to use because you can build a GUI easily with Python, for example. Okay, a quick application before I finish my presentation. So as I said, we use the JConT-LP and the 15 megawatt wind turbine. So this is just to show off a bit what we can do with such a framework. We've used some simple environmental condition, a bit similar to the one presented in the source of Kutai presentation. So a wind speed with 11 meters per second, close to the mean wind speed of the 15 megawatt to have a maximum pitch angle of the turbine. And some range of design variables for the optimizer to look at. Some constraints, so on the tower bending moment and dynamics of my system. And some GA parameters, so an initial population of 10 individuals, final of 1,000, and a number of generations for the optimization to go on. Those are the optimization curve, so it's nice. We minimize the cost of the thing, so okay, it's cool. And we see that at the beginning, constraints are not respected and then tend to smooth out during the optimization. This is the density of the design variables. So just to show you a bit where the algorithm looked throughout the optimization. In black is just, so this is the optimized JConT-LP. In black is just the steady position, and in blue is after dynamics were computed, so mean offset plus the little part of the dynamics coming from the spectra of the response amplitude operator of the whole system. Those are the optimized design variables, and I think I'm a bit rushed by the time, but I will go to my conclusion, and then we can come back with questions after if you want. So we studied floating offshore wind turbine and multi-use components through the JConT-LP, and also substructure design optimization. We developed an efficient optimization framework, so combining all the characteristics I was just showing lately. We modeled the JConT-LP using the 15 megawatt wind turbine in the frequency domain and assess its dynamic. We found some optimized design variable, minimizing material costs, also verifying constraints. And I broadcasted some collaboration and ESR work, so that's pretty nice. There are quite a few outlooks, which I will just maybe skip and we can come back to after the questions. But basically it's to build on what was already done. I want to acknowledge the EU, but I do also want to acknowledge you, because thanks to the EU, we had a wonderful project, but it wouldn't have happened with all the ESRs and Sandrine and Flora and the management team. So that was pretty nice. And this is my source. And if you have any question, I'm willing to answer it.
Thank you, Victor.
Thank you.
So are there any questions?
Thank you very much. Nice presentation. So you were mentioning that depending on your algorithm, you might not find the optimum, yes. Which I would say it's kind of problematic, right? Like if you're looking for the best solution. What if you would like do 10 times the same? You will run 10 times the algorithm. Would you in the end have 10 times the same results, or you would expect to have like different type of structure, like somehow similar but exactly not the same?
Thanks, Thomas, for your question. It's actually a quite interesting question and highlights a bit one of the advantages of using the efficient algorithm I was talking about. So this is one drawback with a genetic algorithm, is that sometimes it gets lost in one local optima. And so if you run, for, like you said, 10 times an optimization run, you might end up in different local optima and don't get the same results, optimized results in the end. That's why usually when we present results with genetic algorithm, you tend to show a mean or like a compact form of like maybe 10 or 100 runs of optimization to co-op with that. With our genetic algorithm, we also, you saw on the result that I show, we pushed a bit the boundary. We put a lot of generations for the algorithm really to go look through a bit all the design space and to really end up in the global optima of your thing. But with the addition operation and in the genetic algorithm, it allows you to look for more individuals. So you go look for a bit almost everywhere in your design space. But if you are too close to a point where you already passed in looked in the past, you are not going to compute the time-consuming numerical analysis to get objectives and stuff. And that's where you save time and make sure that you look almost, don't look in some place of the design space because you have information of the previous iteration. And by this, you kind of prevent of not getting lost somewhere that you might not get lost in another optimization run, but you get a global picture. And if you repeat this with many runs and also going successively in more and more generation, you see that this addition operation prevents actually this problem. But also you have to leave space to your algorithm to really converge or like be sure that you looked through design, the whole design space. But yeah, runs in using genetic algorithm, you tend to make many more runs to make sure that you didn't get lucky and end up somewhere with your optimization. I hope I answered your question.
Thank you. Alani? Yes.
And thanks a lot for the nice presentation. Do you think that using gradient-based optimization techniques might be a solution to this? To cut back this randomness of the solution, the final solution that you find in your genetic algorithm?
It could, but that's nice when you know, for example, you know the objective function you're trying to minimize. So with a gradient-based solution, so you need at least an expression of your objective function. So when it's a nice objective function and also a simple model, so one could say that the frequency domain approach that's used, things are linearized and actually you could find the derivative of your objective functions. But when you start including many more design parameters, so here it was only 3, but if you tend to include more and include material cost and then LCOE representation to have a better picture of the cost of your system, and also you include dynamic constraint and maybe other type of constraints which might bring non-linearities to your optimization problem, and then you get stuck. So I would say it's problem dependent, and we saw with your presentation, for example, that it was possible to use gradient-based optimization. It's just another type of optimization with pros and cons, and in the state of the art we performed, we saw that with floating offshore wind, non-linearities are present, and so it's nice to use optimization technique which get rid of that, or at least it's one solution.
Thanks.
Thank you.
Maybe a last question? Yes.
Thank you for your presentation. I have a question about, I think there was one of the constraints was the pitch, and
yes.
You used smaller than 3, and Kutai used smaller than 5. Is it the same pitch?
So, sorry, how much did you use?
5 or 5 degree, I think.
Yes,
so
fine, but they are different platform types. So mine was Spark.
Yes. and mine is TLP, and
Okay.
also, yeah.
Yeah, this was my following up question.
Yeah.
What is the reason?
The reason why I put 3, it was for showing off results. So it was an application to show what you could do with such a framework. Of course, it's an input, meaning that okay, if I put 10, for sure the optimized will be a bit different because it opens a new feasible part of the design space. To know which one is the best to use, the raft numerical model uses the static position plus an estimation of the dynamics, whereas I believe Kutai's model is time domain. So I know that in the verification process of Raft, they verified it against OpenFast, and it has a good agreement. But on some dynamics and also quantities, so for example, tower base bending moment, they had discrepancies within the two models. So that's why also maybe the value of the pitch is maybe not the same. And I guess for the limit of the constraint, this is also up to the person using the optimization framework.
Yeah,
So-
no, I will think maybe it's about, now it's about the substructure, but it could also be that this pitch is a constraint for the dynamics allowed for the wind turbine in the nacelle,
Yes.
something like that.
Yes,
So,
yes.
and then it should be the same
And also,
acceleration or pitch motion.
Also, Kudai was mentioning some references for the choice of the value of those constraints. If you look at the references in the I would say, so in the publication and scientific reviews, well, I don't, if you compare 10 of them, I would say that maybe there are 10 different constraints. And this is, again, I think in the industry, I don't think it's a public defense of hiding those numbers, but it's something that maybe constructor of substructure or developers might want to keep a bit, not secret, but to themselves. And so you see it in the references, it's quite a bright scope of different parameters. Also, I think it allows you to say, okay, like this I can show off my nice results according to this pitch. Because it really is an input, and the solution, the context between the solutions is not inputs dependent, but inputs do influence the way the algorithm will work and also the solutions you get at the end, because it opens, like I said, other parts of feasible or unfeasible parts location of the design space, I would say.
Okay,
You're
thank
welcome.
you.
Thank you so
Victor.
much.
So let's thank again the 3 presenters of the first session.
Thank you.